Good afternoon, and welcome back to the 5-day faculty development program on GNSS NavIC and applications. And we will start our first technical session, uh, obviously with my overview lecture. Let us start. It's sharp 12 o'clock, and within minutes we will be starting. Thank you very much for your interest in our course. And I would request everybody here, just one thing, many of you have entered through your official designation ID. So for the attendance, it will create some problem. So I would request everybody, because it will be a 2-hour session. So kindly type in your name as you have entered in your registration in the Auto portal. Kindly type in your name so that we can keep track of the attendance, which is mandatory. 80% attendance is mandatory. That means any participant should participate for at least 4 days. That is mandatory, what we have to upload afterwards. So with that words, thank you once again and welcome back.
Good afternoon, Joydeep sir.
So
please continue, sir.
So good morning to all of you. Now this is the first day of this 5-day faculty development program on GNSS and NavIC applications, sponsored by AICT Training and Learning Academy. So the first lecture will be delivered by Dr. Anindo Bose. So Dr. Anindo Bose is working as Senior Scientific Officer in the Department of Physics of the University of Burdwan, West Bengal since 1996. I am also the student of Dr. Anindo Bose. He teaches in MTech in Electronics and Communication Engineering Microwaves and MSc in Geospatial Science course. He is an alumnus of National Physical Laboratory, New Delhi, and International Space University ISU, Strasbourg, France. He is recipient of Ursi Young Scientist Award, senior member of International Union of Radio Science Ursi. He is a fellow of Institute of Electronics and Telecommunication Engineers, popularly known as IT. He is also a member of ASI and ISRS. Currently, he is serving as the chairman, IT Burdwan Subcenter. His research interests include global navigation, satellite system, GNSS, microwave antenna and communications. He has completed and is working with several sponsored R&D and manpower training projects sponsored by Government of India agencies. He is a convener of Industry Institute Partnership Cell IIPC and Career Guidance Cell of the University of Burdwan. He is a consultant to the Indian GNSS industry. So with these few words, I invite Dr. Anindo Bose to present his lecture. Dr. Bose, please.
Thank you very much, Jaydeep, my colleague. Thank you very much for your kind introduction. And let me start my presentation right away. I think you can now see my presentation. So once again, on my personal behalf, welcome to everybody. So my topic, which I have chosen, is Introduction to Global Navigation Satellite System, GNSS. I will try to give you a basic overview on all the topics which will be discussed in this workshop, and to introduce the different aspects of GNSS. But before we start, the disclaimer is the views and opinions expressed in this presentation are completely of mine, and they do not necessarily represent official policy or position of the University of Burdwan or any other agency. So the agenda would be like this. First, navigation, the art and science of knowing location. Second, the concept and the implementation, different GNSS segments. Then GNSS measurements and errors. I will just touch upon this one. GNSS positioning techniques and a comparison in between them and where they can be applied, GNSS applications, and I'll try to touch upon the global GNSS business issues and future trends. Okay, navigation is a tool for survival and progress. Our ancestors, when they used to go out from their caves for hunting, if they do not know that where they are and in which direction they have to come back to their caves, obviously you can understand that they would have been killed during the evening or late night by animals or due to the huge cold. So the basic tool or need for survival were to know where I am and in which direction should I move. Of course, it was a basic need for survival. Early navigation techniques uses celestial bodies and landmarks, as already has been mentioned by Honorable Director ITSR, Dr. Rafasha. Our ancestors used sun, moon, stars, and obviously on the in the daytime landmarks. For example, the mountains, the trees, etc., etc. Still, what we use today when we go from one place to other. Eventually, but of course, you can very well understand that navigation using celestial bodies and landmarks, they have got their own disadvantages. In a overcast day, cloudy day, or during the evening, we cannot see the celestial bodies and landmarks, so navigation becomes impossible. So eventually, the magnetic compass, it reduced the man's reliance on celestial navigation because now it was possible to find out the north direction and with respect to that, other directions. So direction finding was possible, but not other things. Then came the sextant, which was developed and refined over several centuries, made Polaris and its celestial neighbors considerably more useful to navigators on the high seas. It was a very, very interesting story. Latitude from a point can be measured through measuring the elevation of the pole star, and longitude can be measured by measuring the speed of the vessel and the time elapsed. So there are the two challenges. Obviously, how to measure the velocity or the speed of a vessel. Definitely, it's a maritime for maritime applications. So how to find the speed of the vessel, and secondly, the time. The measurement of time is very, very interesting history. I'd request all of you, if you get some time, just go to Google and search how the measurement of time, the art of timekeeping. It was another very, very interesting topic, and I'd rather say a journey through the history of science. So using the time of travel into the velocity, one could measure from a known point how much he or she has moved in the east or west direction. So measurement of longitude was possible. Obviously, during the World War II, ground-based radio navigation system came into widespread use, and it was soon learned that ground-based transmitters could provide reasonably accurate navigation within a limited coverage regime. That is an interesting point, that within a limited coverage regime. I think most of us know it very well, that a radar transmits an EM signal. The EM signal reflects back from a target. The time of travel is measured. Once again, note that time of travel, measuring the time of travel, that means time measurement is a very, very important term here. By measuring the time of travel and multiplying it by c, the velocity of light, one could find the round trip distance divided by 2, and I could find my distance from a known location. Okay, so it was the first electronic navigation system. So radio-based or electronic navigation system aids were radars, Decca, Omega, and long-range navigation or LORAN. It was the earlier navigation system. But all these navigation systems had their own disadvantages. The main disadvantage was the coverage. The coverage was limited within a few tens of kilometers or hundreds of kilometers. Pan-global or over a very, very wide region, a pan-country finding location was very difficult. But the second problem was the accuracy, precision. That the accuracy and precision using the electronic navigation system the stakeholder was getting, that was limited to order of few meters or order of few kilometers. And people had to be satisfied with that one. But you can very well understand that people were searching for tools for more and more accurate and precise location finding technique. So first problem was coverage. Second problem was precision or accuracy. Third problem was how much one can depend. Okay, so dependability. So for this one, the electronic based navigation system, they were defined, they were redefined, they were refined, and ultimately we entered into in the 80s of the last century, we entered into the era of satellite-based navigation. Just like a satellite-based communication system, in case of satellite-based navigation system, the satellites are transmitters of signal. The transmitters in the payload of the satellite, they transmit certain signals which are received on the surface of the Earth or very near to the surface of the Earth, and in some cases, obviously, away from the surface of the Earth. And by proper measurement, the distance between a satellite and my location is found out. So I would use this very simple equation to start our discussion. So Global Navigation Satellite System, GNSS, it can provide highly precise, reliable location information, location that is position, velocity and time information at any point of the globe, anytime using signals from satellite. So the previous problems of coverage, so any point of the globe, secondly, accuracy, and thirdly, reliability, that has been taken care of by an ensemble of satellites transmitting signals, and we, the users, using the signal for knowing our location. So if we take this very easy diagram here, we are taking help of 4 satellites, so 4 satellites transmitting signals, and here it is my location, which has got coordinates in a 3-dimensional space with respect to the center of the Earth. It is X, Y, Z. Okay, so all the satellites, their locations are, say, for example, this one X1, Y1, Z1, X2, Y2, Z2, X3, Y3, Z3, X4, Y4, Z4. Similarly, Xn, Yn, Zn for n number of satellites. So now, by some means, to start with, let us take that by some means we are measuring the distance between the satellite and myself, and it is called range, or in more appropriate term, we call it pseudo range. So we are measuring the ranges of 4 satellites together, and to know my location, I need to know 3 unknowns, X, Y, and Z. So for knowing 3 unknowns from elementary algebra, we need 3 equations. So we are creating a set of 3 equations where it looks like this: Ri equal to xi minus x whole square, yi minus y whole square, zi minus z whole square, whole root minus b. I'll come about the b term afterwards. Okay, so this is a very, very basic equation. So on the left hand side, we have got a measurement, and on the right hand side, we have got a few data. The data xi, yi, zi, it is coming from the satellite through the navigation message what the satellite is transmitting. So we can form the equation. So set of 3 satellites, and if we can solve them, we can solve for x, y, and z. It looks like very simple. But the problem is, once again, we have to measure the time of travel from the signal from the satellite to myself. So measuring the time of travel means there 2 clocks are associated, one at my end and another at the satellite end. And as because they're decorrelated, they're not in the same system to start with, so they have got their own biases. That means the satellite clock and my clock, they are in error. Either the satellite clock is leading or it is lagging. So the 4th unknown becomes delta t, that is the time lag between the system clock, satellite system clock, and my clock. So there are ultimately 4 unknowns, and when we multiply this delta t with c, it converts into b. So there are 4 unknowns. To solve for 4 unknowns, we need to create 4 equations, and to create 4 equations, we need 4 satellites together. We need 4 satellites to sit together simultaneously. Okay, so the basic challenge now comes down to, we have to make a good measurement, and number 2, we have to see, or we have to get satellite signals from at least 4 satellites together. Okay, that is a very basic. With the help of constellation of satellite, what has been given here, two examples, the top one for GLONASS and the bottom one for GPS. We could now get at least 4 satellites. I will talk about this India, from India, at any point of time, we can get up to say 50 satellite signals. So we are in a requirement of 4 satellite signals, but we are getting altogether nearly 50 satellites altogether because of the typical geographical location of India. So now once again, just recall that we have to make a measurement, good measurement, that is the left-hand side, RI, and on the right-hand side, we have got data. Some of the data is coming from the satellite, some of we will solve from the algebraic procedure. Right. Now the problem comes how we can cater the need of simultaneous visibility of 4 satellites, and about the measurement I will come later. Any GNSS system, it has got 3 segments. The satellite segments can be subdivided into 3 parts: the space segment, which consists of satellites; secondly, the control segment, which the control electronics by the system operator; and third is the user segment, lots and lots of different types of satellite receivers. If we take the example of GPS space segment, in case of GPS, I think Sri Atul Shukla ji in the post-lunch session today will talk more about this. Just to give you some idea that, well, it is a 6 equally spaced orbital planes in medium Earth orbit, some 20,000 kilometers. Each plane contains 4 slots occupied by baseline satellites. So it's a 24 satellite constellation, but there are more satellites now. Okay, and so this is how the constellation would look like. And secondly, I have taken a simulation from Hyderabad, nearly in a central position of India, and how the satellite tracks would, ground tracks would look like. So this is a particular one particular type of constellation. The second constellation, because it's a different type of constellation, it's a GLONASS constellation. It consists of 3 equally spaced orbital planes in medium Earth orbit. It is a 19,000 kilometer height. And the third constellation type, so GPS and GLONASS, both of them are global constellation. And the third type is, I'm talking about, that is the NavIC or IRNSS space segment. It's a regional system, and it's a 7 satellite regional constellation. And from Hyderabad, the ground tracks would look like this. Once again, I think we'll get ample opportunity to hear about NavIC in the post-lunch session today. Now we are living in a multi-GNSS scenario. Multi-GNSS scenario means we know that the forerunner in the satellite-based navigation system is GPS, and after that came GLONASS, the global constellation. Then came Galileo from the European Union, and BDS or Baidu from the Chinese, is the Chinese counterpart of the global constellation. And Baidu is a very typical and interesting constellation, which will be taken care of by Atulji, what I came to know. And there are 2, as of now, there are 2 regional constellations. QZSS from Japan, which will be dealt by tomorrow morning by our old friend Dinesh, and IRNSS NavIC, our own constellation system. And obviously, there are a few satellite-based augmentation systems. I will talk about this, just touch upon. There was from the US, the MSAS from Japan, IGNOS from the Europe, the Gagan, our own satellite-based augmentation system, then SDCM from Russia, and BDS BAS from China, and KSS from Korea. So you can see there is much interest in developing own constellation and own satellite-based augmentation system. I think for the young researchers here, or the PG students who are present here, for them, a question should come into their mind: why? Putting a satellite into orbit and maintaining it for a long time, it's a very costly affair. Why so many? Because nowadays anybody having a mobile phone, he or she would have access to GPS signals, and we can find modest accuracy. So why so many countries are developing their own system, either a global or a regional system? Why? So I keep the question open, at least for the starting presentation. I think at the end of this workshop, we will come to know why the competition and the effort is there for many countries. So as of mid-December 2020, I have not changed it from 2020, because in the next lecture, you will find how the scenario has changed a little bit. The global system, which is operational global system, there are 32 active satellites in sky, out of which 29 are operational. It was there. In case of GLONASS, 28 were active, and 20 were in the constellation, and 24 are active. Galileo, out of 26, now it is 26. At that time, it was 25. 25 active, 25 satellite in the constellation, 22 are active. And for the COMPASS or BIDU or BDS, 49 satellites are in the constellation, out of which 44 are in operation. In the regional systems, 4 out of 4 in case of QGSS, Japan it's operating. And in case of NavIC, out of the 7 satellites in the constellation, 6 are in operation. So we can very well understand that more than 120 satellites now in the sky for our use. Now, I just want to give you a glimpse of the GNSS satellite and frequency allocation. Obviously, all the GNSS systems, they transmit signals because we catch the signals using proper electronics. Catching the signals, we distribute the data from it. And secondly, using the signal, we make the measurement. So there are basically 3 components. So first is the carrier component, second is the code component, and third is the data component. The satellite data, a very low bit data rate. Second, the code. It may be a slow or fast data, and ultimately the carrier signal. So I have given just one example of how the GPS signal is created. So this is the navigation data. It is superimposed on the CA code or the P code, the precise code or course acquisition code, and they are now put into the L1 or L2 frequency, and LR or L2 outputs are there. Now there are many other civilian frequencies that there. And I have taken this picture, just the representative picture from the earlier ESA website, where you can see. So this is the frequency planning for GPS. This is CDMA, and this is for GLONASS. This is the existing FDMA, and this is the proposed CDMA structure. This is for Galileo. This is for COMPASS. There are 2 plans, and this is for QGSS, and this is for IRNSS. The beauty of IRNSS is not only in the L5 band, we have also got presence in the unique S band. Still now there is no other presence in the S band. But this is, don't worry, this is just an example. This is just an example to give you some idea that the whole spectrum in the L band, it is populated by GNSS signals, which gives us, the users, number one, the data and the scope for proper measurement. Now the GNSS control segment, this is example. So there are many stations over the globe for GPS, over the Russian territory, and also there are 2 stations in the South America now for the GLONASS operators. And also these are the stations for Galileo. Once again, you can see there are global monitoring stations, and these are the NavIC stations, and also one NavIC station is being NavIC control segment stations scattered over India, and in Novosibirsk, Russia, another station is being proposed. The control segment elements are used for concurrent and continuous signal monitoring, quality control, correction if required, and once again retransmitting the correction signal into the satellites. So the control segment is beyond the scope of our discussion and beyond the scope of our reach. It is completely controlled by the system operators. And ultimately the GNSS user segment. The GNSS user segment, they consist of GNSS receivers of varying cost, capability, and complexity. So you can see here on the top, you can see the very costly geodetic grade receivers. But here you can see the handheld receiver basically used for, say, hitchhiking and trekking, not precise applications. These are used for very, very precise applications, and mainly for geometric applications, the research purposes, etc. And also they include the special purpose receivers. They're very costly. The cost line comes around, along with the antenna, very special purpose antenna, cost line comes around 15 to 20,000 US dollars. Okay, on the right hand side, now the newcomers in the market over the last couple of years, maybe 3-4 years, are the very small, low cost GNSS receivers. I have shown you a few examples, and in the hands-on session, members of GNSS laboratory, we will try to give you some examples of the advantages, and how they look like the low-cost receivers. And from application point of view, the low-cost receivers are very good candidates, a competitive candidate to even some of the very good quality receivers without much compromising to the cost, but at the same time saving a lot of money in terms of cost. For example, this particular fellow on which I am moving my cursor, it's a product from U-Blocks, and the cost comes around less than $100. And this one, it comes from NavIC. So the cost is around $60. So here I was talking about some 15,000 US dollars, and here I'm talking about $100 US dollars or so. So you can find out the difference in cost, obviously with some compromise in the performance and capabilities. But obviously, mainly from application point of view, application development point of view, they're very good candidates. And at the center, I have shown a few examples. I'll talk about later. That a few examples that how the mobile phones now can cater the need of finding our geolocation, or they can be used in many cases as a complete GNSS receiver. Once again, in our hands-on session, we will try to give you some examples, some glimpses, and some exercises that how you can use your mobile phone as a GNSS receiver, as a data logger, and even in some cases, GNSS data processor. Now let us come back once again to the technical side of the GNSS. So just to recall the previous equation, what I mentioned in the earlier slide, that on our left-hand side, we have got Ri, that is the measurement of range or pseudo range, number one. And on the right-hand side, we have got certain data. And now we know the data we are getting from the satellite signal by distributing the very low speed, the 50 bps data. We are getting the values of xi, yi, zi, along with other parameters. Now, how we can measure the range of a satellite, which is very, very important for creating that particular equation. So the what are the typical GNSS measurement a electronic system or a GNSS receiver can make? A receiver channel typically provides the following measurements. First, the pseudo range using code P, they uses delay lock loop, the Doppler measurement using carrier phase measurement, the phase of the incoming signal. So on the right hand side, I have given both the code, the green one, and the carrier, the red one, using phase lock loop, the carrier phase measurement. Then the carrier to noise density, that means what is the signal strength in terms of C/NO. These measurements are raw measurements. So using this, a receiver, these measurements after some manipulation, mathematical manipulation, and obviously we need very, very complex electronics to convert these raw measurements into a user understandable parameter, right? So the designing and creation of a receiver is a challenge and a completely altogether a rather a very big issue and a topic in case of GNSS measurements. I hope in the session day after tomorrow, Dr. Ivan Petrovsky from IP Solutions, he will be talking about these measurements and the development of receivers starting from a software-defined GNSS receiver. Now, with this raw measurement, after some manipulation, most receivers generate single-point navigation outputs. That is position. So if I can measure two positions over 2 times, say for example, P1 position 1 at time T1 and P2 position 2 at time T2. Now we know the difference in time T2 minus T1, and we know the difference in location P2 difference P1. So by dividing P2 difference P1 by T2 difference T1, we can find out the velocity. And once again, we can find out the direction or the heading of the module or the GNSS receiver. So we can get the position, velocity, heading, etc. And of course, timing. Dr. Banerjee, tomorrow afternoon, we'll talk about the timing aspects of the GNSS, how it is important for measurement, and also how, as a product, the GNSS provides us time and how it is very important for global business. Now, a GNSS receiver, that is a multi-channel receiver, a multi-channel electronic device. It ranges from maybe some 30, 32 channels to nowadays more than 800 channels receivers are available in the market. So sometimes the question is asked, why so many channels? Most of the receiver manufacturers, they want to make their product future-proof, because you can see over the last 20 years or so, so many, we started with an idea that we need only 4 satellites, so 4 channels should have been sufficient. But we have come into a position that from India, we are getting 50 satellite signals, so we need at least 50 channels. Now, if we want to get S-bus signals and other signals, so channels are required. And at the same time, for enhancing the processing speed, measurements are multi-channels are kept in a receiver, and measurements are done in all channels simultaneously. The time at which a set of measurements is collected at the receiver end is called a data epoch. Okay, and it is generally synchronized with the GPS time. And I have already told the data is data rate. That means the data, the satellite delivers our data at a rate of very slow speed data up to 50 times per second, that is 50 bps. It consists of many things other than the satellite location itself, the location of the approximate location of the other satellites, the satellite health condition, defined ionospheric and tropospheric correction parameters, etc., etc. Many information comes from the satellite data, but the 50 bps data is sufficient for the purpose. Now, to measure the time of travel, we take help of 2 types of measurements. The 2 types of measurements are called the code and carrier phase-based GNSS measurement. The first one, the code-based measurement, and the second is the carrier phase-based measurement in case of GNSS. Each satellite in case of GNSS, they transmit PRN code, pseudo-random noise code. The PRN code is used to differentiate satellite signals and to provide signal timing information for the range measurements. So each satellite have their own PRN code, as in the case of GPS or Galileo, or all the satellites have the same PRN code, but the difference in frequency, as is the case of GLONASS. So in case of CDMS systems, for example, GPS or GLONASS, GPS or Galileo, each satellite transmit their data, which is modulated with different PRN codes. So our receiver channels get the data, now matches it with the locally generated replica of the codes, and when one-to-one match is occurred for a particular PRN code, that particular channel understands, okay, now we are getting data from satellite PRN, GPS satellite PRN number 26. In other case, in case of a GLONASS channel, the GLONASS satellites keep on changing the frequency, and for a particular designated frequency, when the frequency matches, it understands that, okay, now it is tracking GLONASS satellite number, say, 7. So you can very well understand, using GPS and GLONASS together in a system, it is another challenge for the system developers where we want to use the multi-GNSS signals together, for example, GPS and GLONASS. Another GPS Galileo is a bit simpler because both of them uses the very same type of multiple access. Now, code-based results. So what is done here? So take the right-hand top picture. So this is a particular PRN code, pseudo-random noise code, 0s and 1s. They are coming from the signal satellite, and it reaches us at a time delta t. So what's happening here? In the receiver, we are creating the replica of the very same code, one after another. For example, I'm trying with PRN 1. Now it's not matching. The cross correlation is not matching. Then with 2, not matching. With 3, not matching. So with 4, it's matching. No, now I know that, well, the signal is coming from satellite 4, satellite PRN number 4 of GPS signal. Now, as because the signal has traversed this distance of say 20,000 kilometers from the satellite to reach my receiver or the antenna front end, so it has taken some time to reach from here to here. Now, what is done? My replica of the code-based measurement, in case of code-based measurement, my code replica has to time shift so that a one-to-one match with the code transmitted from the signal and the code generated at my end, they matches perfectly, and the cross correlation value becomes quite high. And in the receiver, we measure what is the amount of time delay or time shift we have to provide in the local signal so that a one-to-one match occurs. And the time delay, you can now understand the time delay, it is the responsible time delay for the satellite signal in reaching from this point to here. So the time delay of the signal in reaching from here to here equal to the time delay what I have given into my signal for getting a one-to-one match with the transmitted code and my code. This is the time delay this is the same time delay. Thereby, we can measure the time delay of the signal in reaching from the satellite to my receiver front end or the antenna front end. And when we multiply it by C, it becomes the range. Now we have to make some correction because of this is the GPS time or the system time. So we have to make some correction. This is the system time mismatch between my system and the satellite clock system. And after that correction, we get a proper range. So we can understand that the code-based results, they are unambiguous, but the precision is limited to a few meters. So the solution, what we get, so we get Ri, similarly we get R1, R2, R3, R4, and after getting all four equations, if you think of the previous equation, R1, R2, R3, R4, we are getting on the left-hand side the measurements, the measured values of say 20,000 kilometers, 20,000 something kilometers like that. And the right-hand side, we have got X minus the location of the first satellite, location of the second satellite like that. So we have got a set of 4 satellites, we solve them together, and ultimately we come out with X, Y, Z, and we convert the X, Y, Z into more understandable parameters of latitude, longitude, and altitude, and it is being displayed on your screen or being output from your receiver to feed to other systems. But increasing number of applications, as I already told, the precision is limited to few meters. In many cases, we need much more higher accuracy, order of maybe a few centimeters, even a few millimeters. How to achieve that? To achieve that, the next measurement technique is called the carrier phase-based measurement technique, which I have shown here. That is the measurements of phase of the carrier wave. So already I have told the signal is transmitted using signals in either L1, L2, L5, etc., etc. So L-band signal that is coming. So this signal, because of its higher frequency, they have got much lower wavelength. Now what is done, if somehow we can measure what is the total number of cycles of the carrier phase that has elapsed since the signal has been transmitted from the satellite and it has reached me. For example, it would be, first part would be a complete cycle, say n number of complete cycle plus some fraction of a complete cycle. So now we have n plus, say for example, 0.75 into capital N. Okay, so n plus 0.75 capital N. So these are the total number of cycles the frequency, that means the carrier frequency, has completed in reaching from the satellite to my place. So if I now multiply it with the wavelength of the carrier signal, I would get much more accurate range from the satellite to myself. But there is a catch. You can very well understand that measuring a signal of a few wavelength of few centimeter accurately, it's pretty difficult and very, very difficult. So I'm telling like this, the phase of the carrier wave can be made to measurement can provide a centimeter level or better accuracy, but the measurement is ambiguous. There may be error. While I'm measuring, say, 20,225 cycle, I may miss a few cycles. I can add up a few cycles. So the measurement error creeps in more frequently than the code-based measurement. As the total number of cycles between the satellite and the receiver total number of cycles of the carrier phase of the carrier signal, it is unknown, and we have to solve for this one. So if we look into, if you go to any GNSS textbook, this is a very basic measurement equation. At this time being, just let us see what are the components present here. In case of code-based measurements, this is the observation P. It is C into delta T. The time of travel consists of the pseudo range. Also, pseudo range consists of the geometric range, the orbital errors. That means the satellite is giving us xi, yi, zi. But obviously, there are certain errors in measuring their exact orbital values. Secondly, the position vector of the satellite vehicle and the receiver. But the position vector of the satellite SB satellite vehicle is known. Then the satellite clock offset, that means the satellite clock errors. Then the receiver clock errors. Then the ionospheric delay and the tropospheric delay. And there are different types of noises, which is obvious in case of any electronic measurement. So the error noise value can range from 5 to 200 centimeter, and code multipath, because of reflected signal from other sources, it is below some tens of meter, etc. So this is the very basic observation equation. So the component I want to not the equation, but I want to draw your attention to the terms of there are certain measurements and certain errors. So to enhance, it is very clear that to enhance the quality of our solution, we have to take care of the errors. If we look into the GNSS carrier phase-based measurement, once again, the basic equation looks like this, quite similar to the previous one, but some other terms comes here. That is the lambda n, that is the wavelength of the frequency used, that is about 20 centimeter. And n is the total number of cycles, integer number, and we have to solve for the ambiguity that we have made the measurement while measuring the total number of cycles of the carrier frequency from the satellite to our receiver end. And also noises are there. Here also you can see the ionospheric and tropospheric terms are there. So these are common. Ionospheric terms, the tropospheric terms are the different types of error. You can very well see here the noises here are much lower, 1 to 5 millimeter, and the multipath errors comes around 0.25 meter, which is much lower than the code-based measurement. So from these two slides, it is clear that the carrier phase-based measurements would provide us much more accurate solution, but the problem is it is complex and much more error. Measurement is much more error prone than the code-based measurement. So resolving or estimating the carrier-based ambiguity is the key to achieving precise positioning with RTK or PPP. I will talk about this just to touch with, and tomorrow or day after tomorrow it will be dealt in a much more detail. So RTK, the real-time kinematic, or PPP, the precise point positioning, are the two positioning techniques what you use in case of GNSS. The two methods used for different techniques to achieve this, but both uses pseudo-range mitigation of position errors, either by relative positioning or by correction data, and multiple signals observation to find the ambiguity term that fit best with the measurement data. So already I have introduced you to many of the much complex issues of the GNSS technology, which one must understand. Now I'm directing my words to mainly the young researchers and the PG scholars. So one need to develop a very good understanding of the basic mathematics to understand very clearly that how the GNSS measurements work. But being the very fast lecture and the overview, I do not want to go in deep of these topics. Now comes already I have told. So if you look here, I've taken this from one of our observations. So you can see the red ones, the blue ones, and the green ones, their position solutions. On the right here, on the x coordinate, we have shown the longitude in degrees. and the y coordinate, we have shown the latitude in degrees. So we are taking measurements during cyclone day Amphan, which occurred last year in May. So you can see the position solutions, they're scattered. And the amount of scattered, you can see one magnitude here is around 2.2 meters, and in the y direction, it is 2.6 meters. So if you take here 1, 2, 3, 4, nearly 5, so more than 10 meters in the longitude, and around 1, 2, 3, nearly 7 meters in the latitude. So here you can see the white ball and the cross, they are the precise coordinate. So the question marks come in our mind. Why? It's a mathematical problem. So we are getting some data, making some solution, and after solution, I should get at least a fixed point. Maybe there is error, but we should get some fixed error. But the problem is, as I already told, there are different types of error, what comes inside the GNSS measurement, and most interestingly, they keeps on changing with time. And in many cases, we do not fully understand them well, so that using a model, we can get rid of them. So first of all, let us see what are the different source of errors. And when we understand what are the different source of errors, we will try to mitigate these errors and using different positioning techniques. I think Dr. Shweta Shah from SBNIT Surat will be talking more about the GNSS error sources and the mitigation techniques. But to have a general idea, so this is our system. So these are the GNSS satellites. The signals are coming through, in case of GPS, some 20,000 kilometers. In case of NavIC, some 40,000 kilometers. It is coming through the atmosphere, through ionosphere and troposphere. And here are our GNSS receiver. Okay. So there are basic three types of error. First, the satellite errors. Satellite ephemeris errors, that means the location of the satellites. The satellite block errors. Thirdly, the relativistic errors. The satellites are moving with very high velocity, nearly 11 kilometers per second. So relativistic error will creep in. And fourthly, the satellite geometry, the scatterness of the satellite in the sky. So some of them we can take care of by measurement. Some of them we can take care of them up to certain level by proper modeling, etc. And in our receiver side, we have got the multipath error. Here you can see. So here Doppler is taking place, ionospheric scintillation are taking place, then tropospheric effects are taking place. Signal is being masked by, say, natural or man-made objects, okay, and reaching my antenna. And at the other side, maybe there are some multipath signals which is being reflected, that this is the direct signal which is reaching me after all these effects. And this is the signal which is reaching me after one or more reflections from the nearby objects. And in city limits, it's much more prominent. So these are the errors. And along with that, we have got jamming signals from same in-band or out-of-band jamming, intentional or unintentional jamming signals. So at the receiver end, we are prone with this type of errors. And obviously, because the receiver is an electronic system, there would be receiver noises. So many of these are errors in the receiver level, we can take care of by proper modeling and proper design. But in between lies the ionosphere. The ionospheric delay, the ionospheric scintillation, the tropospheric delay, and the intersystem biases. Each of the systems, GPS, GLONASS, Galileo, etc., they are being developed and governed by individual entities. They have their own priorities and agendas. So they have their own, I would rather say, baseline measurements or basic measurements or reference measurements. And the references differ from each other. So there are intersystem biases. Okay, so we have to take care of, so these are the errors, and we have to take care of, if we want to get better solution, we have to take care of the error source. It is as simple as that. So resolving these errors is the key to enhance performance. The more errors a receiver can eliminate, the higher the degree of positioning accuracy and reliability it can achieve. And receiver hardware and software design and implementation impacts the effectiveness of the error resolution. So there comes the why the cost differs in case of a very low cost receiver and a geodetic receiver. That's why they use different types of hardware and software implementation to take care of the errors. And that's why the cost enhances because of their proprietary hardware and software capabilities. For the beginners, I'll tell you, if you search this, Introduction to GNSS, it's from Novatel, a major manufacturer of GNSS products. It's a fantastic, easy read to have an idea of the whole GNSS topic, how it operates, what are the basic issues, etc., etc. For the beginners, I will suggest this topic. Now, I was just talking about the satellite geometry. So the satellite geometry is like that. For example, I'm the user standing here, and these are the satellites. Okay, so you can see the satellites are scattered over the whole upper hemisphere. I'm getting signals from them. We call it a good geometry. The satellite geometry measured quantitatively in terms of dilution or precision. The better the geometry, better is the solution, and lower is the dilution. I repeat, the satellite geometry is quantitatively expressed in terms of dilution or precision, DOP values. Okay, the lower the DOP, the better the solution quality. To start with, the lower the DOP, the better the solution quality. And how the lower DOP comes? The more scattered the satellite in the sky, lower is the DOP. Actually, DOP is calculated if we can a multi-hadron. That means if we take from my point, if we take unit vectors in the direction of the satellites and create I would say, a multi-hadron, the volume, 1 by volume of the multi-hadron is the DOP value, or the position DOP value. So more scattered is the more scattered are the satellite, the volume of the multi-hadron is better. So 1 by V is much lower, and we get better solution accuracy. So there are many DOP values of understanding. The position, the three-dimensional position, is associated with PDOF value. The measured time, it is associated with the TDOP, the time dilution of precision. The vertical accuracy is the VDOP, the vertical DOP, and overall geometry, it is called geometric DOP or GDOP. In a multi-constellation environment, obviously, you can very well understand that we have got access to signals from many satellites. So obviously, the size of the multi-hadron with its tip on my antenna location, it would be large, so the DOP value would be small, and obviously the solution quality would be better. So here I have seen this is a good satellite geometry. Obviously, we are in a difficult environment. Obviously, the satellite signals are being hindered or obstructed by either natural or man-made objects, trees, high-rise buildings, etc., etc. So once again, only we can use 3 satellites or 4 satellites, so to say. So it's a bad geometry. Once again, for some reason or the other, we are getting signals from only one side of the sky. Once again, it's a bad geometry. But in a multi-constellation environment, getting poor geometry of this type of constellation, it is not seen nowadays. But this type of cases can be, you can see this type of cases while you are using your device inside city limit or inside forest like that. So we made some study in a multi-GNSS during 2016 to 2018, and we have seen that we tell that PDOF values, position dilution of precision values, around 1 or below 2 is a good value. Okay, we tell like that. So what we did, we used all the satellites. What is available from our location, Burdwan? We used all the satellites. We developed a software for calculating the PDOP, and using that one, what we did, we increased the number of satellites. Okay, so in the X coordinate, you can see the number of satellites. So we used 4 satellites. Using 4 satellites, we are getting values you can very well see around 2 or more, which is considered not a good top value. So when we are increasing the number of satellites, we are coming that, for example, after getting say 13 or 14 satellites, which is quite easily available if we use just 2 systems, say GPS GLONASS or GPS Galileo, we are getting a value of 1.2 or 0.3 like that, which is quite good PDOP. And if we go beyond 20 satellites or more, the PDOF value, you can see it saturates. Okay, so even in a multi-constellation environment, it is of point of interest how we can get the best PDOF, and so that is reflected into the solution accuracy being provided by a multi-GNSS system. That is, once again, that means the optimization of the number of satellites used for solution is another challenge, or I'd rather say another open topic for satellite selection for use. Because when we are using more number of constellations together, there are inter-system biases. That is an error that creeps in. At the same time, we are getting advantage of the better geometry, redundancy of satellite selection. If one of them fails, we do not have to bother. So we have to come into certain compromise that how, if we increase the number of constellation and number of satellites, from one point of view, we are getting advantages, and from another point of view, we are getting some more challenges. How to optimize the number of satellites used for solution. Okay. Now, obviously, as we have seen, we have got errors. Due to the errors, we are getting, say, 10 meter by 7 meter scatter of solution. Definitely, our customers, our clients, our applications would demand for much more accuracy. It would demand for maybe within a meter to be a modestly demanding customer or client or application. But in many cases, they want better solution than this. A few tens of centimeters, below centimeter, or in some cases below millimeter, below centimeter, that is a few millimeter level accuracy. So the point is we have to remove the error. The more we can remove the error, our positioning solution would be better, and we can cater the need of our application, our clients, our customers. So the main technique, so now we will start discussion about the main techniques for GNSS positioning. There are basically 3 techniques what is used for GNSS positioning. First of them is standalone, single point positioning, SPS. Second is the relative positioning, and third is the precise point positioning. Okay, so if I look into this one on the right hand side, so GNSS positioning technique, this is the absolute positioning technique, or this is similar to the SPS or single point positioning technique. I have a GPS receiver. I am operating from my location. I put my antenna in a open sky condition. In an open sky condition, it is receiving signal from one or multiple satellite constellation and making the necessary, after the necessary mathematics, giving me the solution. Okay, so let us see what may be the positioning accuracy. So you can see worldwide. So here is the baseline length. That means from my location, this is my location. From my location, how up to what distance the positioning technique is applicable. You can see here, I'm completely independent. I don't have to bother. I don't have to depend upon anybody else. So it is a global global system or global technique. Anywhere on the globe, on the surface of the globe or very near to it, I can put my receiver and get my solution. But the accuracy, you can see it is order of few meters. It is restricted to that one. So on one hand, it has got the advantage of independence, but the disadvantage is quite low positioning accuracy. Then comes the relative positioning. Okay, the relative positioning, there are at least two methods. Number one, the DGNSS, then the RTK, and in some cases, the DGNSS extended version is SBAS or satellite-based augmentation system. You can see here, the accuracy has improved. Using SBAS, it has come down to order of meters. Using GNSS sub-meter, using RTK, we can reach order of few centimeters here. But you can see here, their applicability is limited. Using SBAS, maybe order of 1,000 kilometers or so, maybe pan country. Using DGPS or DGNSS, maybe hundreds of kilometers. Using RTK, maybe some 50, 60 or below 100 kilometers. So we are enhancing the accuracy, but at the same time, using these three methods, DGNSS, SBAS, and RTK, using these three methods, we are having the limitation of the coverage of obtaining the accuracy. So this is the relative positioning. In case of relative positioning, more than we have to depend upon, you can see here, we have to depend upon an infrastructure. So this is me. So this is me, the user, and this is somebody else. I have to depend upon him or her. Okay, he is also making the same measurement, measuring the errors and giving me the error values, maybe free of cost or maybe for some price. It is giving me the correction factors or the correction values. Using the correction values, I'm improving my solution. So that is the basic idea. So this is, I would call it a base, and I am here an user. I'm a rover. So the base is making precise measurements, calculating for the errors, and transmitting the errors. I am getting the errors, making the measurements, and after the measurement, using these errors to improve my solution quality. So this is the basic of the relative positioning. And the third method, it is called the precise point positioning. Precise point positioning, once again, it is quite similar to the, I would rather say it's a blending of relative positioning and standalone positioning. I am here, I am making some standalone positioning. But at the same time, I am getting some products from the international GNSS service, what we call the IGS. I am getting data from IGS, the error values, which is not real time. In this case, I am getting real time correction. But here, I am not getting real time corrections. After some delay or some latent time, I will get the correction factors. And after getting the correction factors, I am improving my solution accuracy. And you can see here we are getting even tens of centimeters. But with proper PPP, we can come down below centimeter, and we are getting a few millimeter level accuracy using PPP service. In the hands-on session, we will try to show you how we can take advantage of the many free of cost complementary online PPP service provided by many global agencies. Now, we have to make trade-offs between the different error removal methods of the GNSS signal. It depends on the user requirement of individual applications, level of accuracy requirement, system complexity. Obviously, system complexity means enhanced complexity, enhanced cost, solution availability, reliability, and most importantly, for real-time applications, the cost. How much cost our client, our user, or our application we can provide. So you can very well understand the absolute positioning. The cost is only due to the receiver itself. Obviously, better receiver, better solution. And PPP, once again, in many cases, only a single receiver is sufficient. Single good quality receiver is sufficient. But in case of relative positioning, we need some infrastructure, and in many cases, we have to create the infrastructure and we have to pay for it. If we come into GNSS single point positioning in a bit more detail, that one of the technique for getting better solution is averaging of the repeated observations. It is not very efficient, but very simple. Now, modeling of the phenomena that is causing the error and predicting the correction values. Obviously, there are standard models, there are standard softwares, but the softwares are very, very costly in many cases. Also, free softwares are also available. We can use those softwares and write our own programs to use the raw data to extract out better solution. Third is use of multi-frequency receivers. Multi-frequency receiver means which can simultaneously use both L5, L1, L2, or L1, L5, or E1, E5, or B1, B2, L5S, more than one frequency measurements. It is an effective way to remove ionospheric error from the position calculation, because in situ, using this elementary equation, part of the ionospheric error, which is the major contributing error, that is taken care of. For example, in case of a dual frequency receiver, the measured relative phase delay can be measured using this one, and we can take care of the measurement delays and get better solution. Next, we can use modernized wideband signals. For example, the L5 or E5A in case of Galileo. I think Mr. Rainer Horn, who will be representing SPA, tomorrow we'll talk about the advantages and the differentiators of the Galileo signals that provide inherent noise and multipath mitigation capabilities, and to enhance the immunity to interference and multipath, so that we can choose a very good location, proper open sky location from where rare chance is there for multipath. That means a complete open sky location for placement of the antenna on the rooftop, maybe on a field, so that the multipath from the high-rise buildings and the trees do not come in. And obviously proper antenna design. Obviously from the ground itself reflected signals should be there. Try putting antenna base plate and choice of antenna. We can get rid of some of the errors, and we get a moderately good or modest SPS position solution accuracy in many applications which are acceptable, but not for all solutions. We can use multi-constellation. We can use larger number of satellite for redundancy, reduce signal acquisition time, improve position and timing accuracy. I told better DOP and better solution. Reduction of problem due to obstruction and improved satellite geometry, I already told. Once again, this is another from our old receiver. It is from a data using a GPS GLONASS, very low cost receiver. So you can see here, this is the 3D solution error, and this is the cumulative percentage of occurrence. So when you are using only GLONASS, you can see in 90% of the cases, the 3D error remains within 30 meters. Okay, it was done in 2013. But using a mixed constellation, this one, we are getting in 100% of cases, we are getting better than 5-meter accuracy. So using a very even low cost accuracy, two constellations together, single frequency, we are getting better position using SPP or single point positioning. So I wanted to give you a feeling. Now let us come into the differential GNSS or DGNSS. So in DGNSS, already I told I need at least two receiver entities. This is the base and this is the rover, the user. The base is supposed to be a high quality, geodetic quality receiver. The base station has accurately known location. How to do it? We will use PPP to find out the location and put the location inside the base. I will try in the hands-on session. The base station receives GNSS signal and calculates the pseudo range. As because it is operating from a very well-known, very precisely known location, now the precisely known location and the instantaneous location, that is the difference between them, is the error. It can calculate out this. The base calculates the pseudo range errors using the accurate measurements. Base transmits the error for the rovers over radio link or maybe internet. Rover receives GNSS signal, calculates pseudo ranges. Rover uses the range corrections, corrected pseudo ranges, improves the solution accuracy. The absolute accuracy of the rover's computed position depends on the absolute accuracy of the base station position. So you can very well understand. The better we know the location of the base, the better would be the correction signal quality, the better would be the solution at the rover. Now, GNSS satellites are in the EMEO. The propagation paths from the satellites to the base and rover pass through the similar atmospheric condition as long as the base station and the rovers are not too far apart. And that's why the limitation of the distance in case of the DGPS or RTK comes into discussion, because the errors comes from the atmosphere. If the base and rover are far apart, so the atmospheric conditions and the base's location and the rover's location, they may not be the same. So the correction factors would not be fully applicable in case of rover. So we would get a degraded solution accuracy. Differential GNSS works well with the base to rover separation up to few tens of kilometers, maybe hundreds of, maybe around 100 of kilometers. But what happened? So you can very well understand that we have to transmit the signal using radio link. Transmitting by radio link, it has got its own limitation. We need huge power. And secondly, the radio coverage for different reasons, also regulatory reasons, we cannot transmit over a large region. So comes the augmentation system. So augmentation system means where we would support the GNSS signal using ground-based or space-based assets. Ground-based or rather space-based systems. Let us go here. So ground-based augmentation system or GBAS. So these are the GNSS satellites. The GNSS satellites, this station is getting data from GNSS satellites, calculates the data, and uploading the data using VHF link to the user. Okay, or it has got some ground-based assets. Using the ground-based assets, these are the network of the ground-based assets. Using the ground-based assets, it is collecting data, making the error signal, creating the error signal, and transmitting it to the user. So it is called the GBus because it's called the ground-based augmentation system. Sometimes it's called local area augmentation system or LAS. It provides differential corrections and satellite integrity monitoring to receivers using a VHF radio link. GBus consists of several GNSS antennas placed at known location as central control system and VHF radio transmitters. GBus covers relatively small area and used for application that requires high level of accuracy, availability, and integrity. For example, in case of the vicinity of the airports. But if I want to supply this data over a large area, for example, over a whole country, then comes the SBus or the space-based augmentation system. Here the idea is quite similar, but the correction data delivery is being done through communication satellite. For example, the communication satellites placed in the geostationary orbits. So here we have got the GPS satellites or the GNSS satellites, which are placed in the medium Earth orbit, 20,000 kilometers. So these are the wide area network reference stations. All the reference stations, they are collecting data, and all of them knows their locations very accurately. So all of them are creating their own set of correction data, and using the upload station, it is uplinking the correction data to the communication satellite system in the geostationary satellite orbit, GEO. So now, as because GEO has a much larger coverage area, so this covers the whole country. So it's sometimes called WAS, Wide Area Augmentation System, or most commonly the satellite-based augmentation system, like that. So any user, anywhere within the network, it would get correction data from the communication satellite, and region-wise, the correction data sets would change. So for example, an user here, it will get the correction data appropriate to this region because of the typical ionospheric condition here. Some user here would get the data appropriate to this region. Similarly, for this aeroplane, where it is getting the data appropriate for this region. So the coverage area is very large. It can cater a very large number of people or the user. But the problem is it uses code-based measurement. So the accuracy is limited. And secondly, one needs a very large infrastructure. Only the federal government can create such a large infrastructure for creating such a facility to its user. For example, in our case in India, we have got the Gagan, which is created by ISRO and Airports Authority of India together, and it is in full operation. So for the cost of the differential GNSS is high, or for large coverage area, SBus may be used. Already I talked about this one. Signal availability can be improved if the SBus transmits ranging signals from its satellites. SBus system include reference station, master station, uplink station, and geosynchronous and geostationary satellite. A large infrastructure is needed, but the problem is till now the SBus system provides code-based measurement and relatively lower accuracy than its other counterpart, the real-time kinematic or the RTK system. The real-time kinematic, which will be talked more detail tomorrow morning by Dinesh, it uses carrier phase-based ranging. Already I told that carrier phase-based ranging provides better solution accuracy, so that is reflected here. So basic idea is very similar. Here we have got the base, here is the rover. We see the very same set of satellites, and using a communication link, the errors are being transmitted from the base to the rover, and the rover uses the raw measurements and the correction values for improved solution. And here also the ambiguity resolutions, etc., etc. It is which are associated with the carrier phase-based measurement, that is also associated here. Another point is, in case of RTK, another very important advantage is, earlier I told that we need to transmit the error signal so the users can use it. There are two methods. Earlier only the radio signals can be used. or in some cases for large infrastructure, the VHF link or the S-bus link. But another method which is much more popular now, it is this one. So here I have shown, so this is the base station. It is collecting data, so creating the error messages. So using the error messages, it is sending to this radio. This radio is transmitting. Here my rover station is there. Rover is getting the raw data and also this transmitted correction data and uses it. This was one method. But you can see here it is written 10 to 20 kilometers. It depends upon the range of the radio it can cover. More important and more popular technique is, why not I pump or I upload the correction message into the internet. Okay, so the base station correction data is pumped into the internet. So anybody, for example here, this user, it has got connection to the internet. It is downloading the correction data from the internet by simple maybe GSM network, maybe using a broadband network, wherever internet is available, it is getting the correction factor. So we can get rid of this fellow, this radio. Obviously, we can get rid of the cost associated. Secondly, we can enhance the cost of the cost of data transmission. But obviously, your service provider, for example, your base station, it should allow you to access the internet data. And this type of correction data message transmission, it is called network transportation of RTCM using internet protocol or encrypt. And the correction data is called RTCM message. Okay, real-time correction message, RTCM. So network transportation of RTCM using internet protocol, it is called encrypt. So it is the encrypt method. This is called the encrypt server, and I, being the rover, is an encrypt client. So the encrypt client should have the credentials to take the service. There are many services, at least there are global players who take the globally provides the error messages, but you can very well understand the global messages will not be applicable for us. We need infrastructure for our country, so that we have got this type of infrastructure, and also paid services. It can be a very good business opportunity in India, so that one can put up core station, continuously operating reference stations like that, and put the data into internet for use of the clients and use of the users. Maybe our government may be a major player, and already plans are there, but I came to know that already countrywide core station establishment has already begun with the support from Survey of India. And you can understand here, your receiver, your rover receiver should have the capability either to receive the radio messages or to access, should have access to the internet. So this is the very basic idea. Good example that okay, so it is a software RTK lib. We will talk about this afterwards. Using RTK lib, our rover receiver, it takes the data, raw data, and the data from the encrypt server as an encrypt client and processes it. It's a fantastic, completely free of cost software. We have done this. I have given some examples. So this is at Burdwan. It is some 60 kilometers away. We have done RTK using the rover. We have compared. This is a high cost rover. It is a low cost rover. So we have compared the performance, and very interestingly, we have got very comparable performance between a $15,000 receiver and a $100 receiver. Obviously, there are certain constants, and here we tested. So if we use a low cost base even, so we are using a high cost base, here a low cost base, here a low cost rover, low cost rover. So here we are using a high cost base, low cost rover, low cost base, low cost rover combination. So different types of combination we are testing in our laboratory, and we are working with ITR in this respect, that how we can bring down the cost for surveying, and our result I think would also be very useful for other applications, including the industries. But there are different types of real-time kinematic. One is called a single-base real-time kinematic, where there is only one base or a network RTK. That means where a chain of core stations, multiple base stations are there. just like our mobile phone, it keeps on switching the control tower when we move forward. As our control is handed over, similarly, the encrypt service is handed over from one base station to another to the countrywide network in Japan, Thailand, and in many countries. Lots of course network is there for network RTK. In case of PPP, precise point positioning, what we call the Formula 1 of GNSS positioning, it removes or models GNSS systems to provide high-level position accuracy using a single receiver. The solution depends on GNSS clock and orbit corrections generated from a network of global reference stations called the IGS network. Okay, a typical PPP solution requires a period of time to converge the highest achievable accuracy, at least 15 minutes or more, and a dual frequency receiver. So here you can see the idea is like this. So the GNSS receiver, it is getting data, and from the network, it is getting the correction data and using it, but it cannot provide real-time data. And you can see the solution is converging within, say, 30 minutes to 1 hour to the best possible accuracy level of centimeters. But here the data is not real-time. It is most appropriate for scientific applications. I must introduce here, for PPP, doing PPP, we get the products, that means the error products, from a global network of a large number of contributing stations. There are a few stations also in India, in Hyderabad, in Bangalore, in Lucknow, and recently started in Port Blair. So these IGS stations, they continuously monitor the GNSS signals, create the correction data, and transmits it free of cost over the internet. So any user can use it. And I would request you, the interested user, to visit this website, igs.org, for better understanding. So there are many online PPP services. They are government and commercial. So free online services are OSPOS, OPUS, NRCan. OSPOS is provided by Geoscience Australia, OPUS by National Geodetic Survey USA, and National Resources Canada, NRCan. So these are the web links. We will talk during our hands-on session. You have to gather your data, how to collect your data, and how to upload it here. And afterwards, you will get back your precise point location, and you can start doing RTK. And the post-processing software, there are many post-processing softwares, but we need Linux dual frequency GNSS data for the purpose. The best example is free of cost RTKlib, which is available from the RTKlib website or from GitHub. GLab, there are other softwares for Gamut, Globe, Track, etc. It's a one of the best softwares. Barn is from University of Barn, but it's very costly. In Indian currency, it is nearly 10 lakh rupees. And also some paid services, for example, Magic GNSS from GMV, an European company. So these are a few softwares or facilities one can use for GNSS data processing. Once again, one can write his or her own program or use this software for GNSS data processing for very precise applications like, say, cadastral plate movement, like that. So with that, let me just introduce a few about the GNSS applications. The basic applications are positioning applications, time transfer, atmospheric research, and different science applications. So everyday GNSS applications, as already told, the first GNSS GPS and GLONASS were developed by the military users. So they are military, for the military point of view, they are developed, but very fast, we the civilian users have outnumbered the military users. Okay. So everyday GNSS applications, here the navigating the cars, in ports, in aircrafts, in railroads, etc., in traffic management, in electricity distribution, etc. So high precision GNSS applications, very, say, for example, dam deformation monitoring, different types of surveys, agriculture, drone movement, etc., etc. During the course of this workshop, other experts, I'm sure that they will introduce you to different types of GNSS ground geodetic applications. I just want to draw your kind attention to the facts that how people are using GNSS. A few examples would give some ideas to your thought process. I've taken the example from UN Nepal workshop on applications of GNSS. It was in Kathmandu during 2016. Many of our friends they presented here. So just take the example. Developing sustainable collaboration model for implementing integrated space-based geospatial disaster management infrastructure, etc., etc. So it's from Tokyo. So for disaster management. Second one, it was a presentation from Nepal, coupling GNSS with web APIs for disaster management. Once again, disaster management. Second, developing a semi-dynamic datum for Nepal Gorkha earthquake. Okay, that means very long-term data measurement, data collection. It is from New Zealand. It's a very interesting. The next one is a very interesting presentation. It's from Bangladesh. On the spot, identification of flood inundation depth from gridded data using GPS-enabled smartphone application. It was from Bangladesh. So my friend Professor Shahidul, he was using his smartphone to collect data and the legacy data about the level of the water up to which the flood water has risen in a particular area. So what happens after that, when the permission for erecting a new house is being given, the mandatory plinth level, that is the base level for creation of the plinth level, from this database, it comes that your plinth level should be at least, say, 3.7 feet for this location, in somewhere 4.1 feet in some location. So in the next flood, their houses are not flooded. So thereby, a huge amount of natural resources, huge amount of money can be saved, mostly for the poor people who needs this type of technology for their livelihood. So it was a very good example. Secondly, here, application of space technology, including the GNSS in healthcare model of Nepal. A very interesting one, another one, habitat suitability of tigers in Chitwan district. So you see another type of use in case of using GNSS. So more applications you can see, tracking the vehicles which is carrying hazmat, that means hazardous material. Anytime it is beyond or ahead of his schedule, SMS is sent to the controller and it controls the driver. Similarly, tracking of people, obviously it has got some other ethical issues. Controlling the livestock. Similarly, already I told the hazmat, etc. If I take examples in sector agriculture, which is very, very important for countries like us, India, Bangladesh, Sri Lanka, and adjacent countries, which are basically agrarian countries. So we have already into the agriculture 4.0 in digital farming era. The amount of land is not increasing, the population is increasing. So we need smart agriculture. Okay, and for smart agriculture, we should measure, and we should use measure to properly utilize the cultivable land for the best amount of yield. I've given you some examples. So this is one example from Thailand, where they're doing how the mechanized farming can help in sugarcane harvesting. Okay, so in this case, it is in 8th Multi-GNSS Asia Conference, efficient oil palm management prototyping. That means how the old palm trees should be cut down and new palm trees should be planted, so that the yield from the palm trees always remains effective. So this type of thing they're trying using GNSS, because the GNSS can measure exact location. So this information can be fed with data from other location. I can give you one example. It was a small project done by our students. So here we are using a controller. So this is the GNSS module with patch antenna, very low cost module. Okay, we are using the temperature, humidity, soil moisture, soil pH. These are the modules. It is collecting data using the Raspberry Pi controller. And after collection of the data using GSM network, this dongle is transmitting all the information, the location information and the condition of the location continuously to the central location. So how the situation changes, the atmospheric condition and the soil condition changes, how it affects the yield, how it affects, is there any relation between the any disease and pest infection with the maybe moisture and the temperature or humidity. So this type of studies can be done, and that can help obviously people of our country, mostly for we are being an agricultural country. Similar example is intelligent transport system, ITS. It is taken from Philippines for public utility bus system. I know one of our friends is present in the in this workshop from Sri Lanka. They are doing a very good project in collaboration with many European four Sri Lanka universities and four European universities. They have formed a consortium and they are working on the using GNSS in intelligent transport system. So another example we have given, once again a very old effort in 2014. What we have done, it was a larger thing. So it was a development board, ARM-based development board. So this is a small, although at that time it was the smallest possible board of what was available here. You can see here. So this is the GNSS board. Okay, so GNSS board, it is taking data here. So this is the GSM module. So it is showing the latitude and longitude when we have put it into vehicle, and as the vehicle moves after every say 1 minute or so, it is updating its location. So this is another example. So more examples will be. I was fascinated to see this influence of GNSS in positioning inventory plots for tree height distribution studies. Another GPS technology for semi-aquatic turtle research. So you can see in many spheres of life, GNSS is being used. Another is disaster monitoring. Some examples: GNSS in tsunami monitoring. Some case studies I have taken it from a Japanese website. Then NavIC is also giving us some sort of facility, some sort of this type of facilities. More examples: predicting landslide behavior through continuous monitoring, preserving a landmark, etc., etc. So I've given the papers from where I've collected the screenshots to give you some examples. Another is QZSS-based disaster alert system. It's a fantastic system. So QZSS, along with your location information, it transmits the disaster alarm to the users. So a GNSS user directly knows whether he or she is in the affected area and in which direction he or she has to move to reach to a safe place. Another example, we have done a survey fire preparedness of a building using GNSS and GIS together. The other example applications of GNSS signals for atmospheric research on the last day. Dr. Nirikar and Dr. Das will be talking about this one, how GNSS signals, I would say many signal sources free of cost from the sky, it is reaching us and it is being affected by the ionosphere. So this effect can be measured, which is a measure of the if anything is being if anything is happening in the ionosphere. Another important effect use of GNSS is world timescale maintenance, how it is done. Dr. Banerjee will talk tomorrow. Two more important topic which is coming up very fast, that is GNSS-based radio occultation. So we have got receivers here. When the GNSS signal passes through the Earth's atmosphere, it gets bent depending on the Earth's atmosphere, and the quality of bending and the amount of bending depends on the nature of the atmosphere. So the measurement of the bending is the measurement of the Earth's atmosphere. So GNSS-based radio occultation is another very popular topic which is coming fast, and many people in our country also. Here you can see. So this fellow is getting signals. It is getting direct signal from this satellite, bent signal. It is getting direct signal from this satellite and reflected signal from these satellites. So number one, this fellow is getting bent due to the effects of the atmosphere, and also the reflected signal bears signature of the atmosphere. So it is getting two types of signals. one from here and another from here, and thereby it can study the effects of the atmosphere on GNSS signal for probing the atmosphere, or to be specific, the ionosphere. So it is becoming another interesting topic for research. Another topic is the GNSS reflectometry, what is called the previous one was being called GNSS RO, and the next one is the GNSS R, or GNSS reflectometry. So if you look here, you can see, so here we have got two antennas, okay, one looking upward, another looking downward. So from the GNSS satellite, this antenna combination, it is getting two signals. One is the direct signal, another is the reflected signal. So depending on the surface, the quality of the surface, whether it is soil, if soil, what is the content, what is the moisture content, the reflectance. So this gets two types of signal. One is the direct wave, another is the reflected wave. If it is not soil, if it is weather, water, so the here you can see it is water. So depending on the height of the wave, the reflected signal pattern will change. Okay, so what is the sea wave height, or what is the moisture content of the soil? This type of research have already been started, and also NavIC-based this type of research has already been initiated. Probably some of the researchers will talk about this. And so here you can see. So this is a GNSS R reflectometer. It is getting signals, direct signals, and getting reflected signals from different locations on the surface of the Earth. Okay, it may be a ground-based system or maybe a space-based system. And by comparison of this direct and reflected signal, it can perform many studies. So you can see it is being used in case of ice. It is used in case of water, for measuring the water level, whether it is calm, whether it is not so calm, whether it is it has got large tides, and also for the measurements of the forest areas. What is the height of the trees? What is the quality of the, what are the types of the trees, etc. What is the density of the trees? This type of measurements are being done. So GNSS-R exploit the reflected navigation satellite signals from water, ice, or land surfaces. Fundamental geophysical properties of the reflected surface can be derived, for example, altimetric height, soil moisture, roughness, which can be correlated with wind velocity and direction above water. The spectrum of applications is manifold and includes weather forecast and climate research. So it is another very important topic in GNSS research, which is coming up fast. It was not so old use. Another use is GNSS INS, that means the inertial measurement unit, IMU, which uses different types of sensors. So when, for example, when this vehicle is in open sky, it is using GNSS. When it is entering into a lane, the GNSS signals are obstructed. Now the INS takes care of, and the INSS is putting it into nearly a good trajectory. And once again, when it comes out of this lane, once again, it is using GNSS signal. So tight, ultra-tight, or loose coupling of GNSS and INS, it is another topic which is being used for many applications, mostly in case of intelligent transport system and vehicle tracking. Now for the last 10 minutes or so, let me talk about GNSS market trends and some issues. So if you go to this particular website, you will find the GSA GNSS market report, which was published in 2019, late 2019, the last quarter. I just want you to concentrate upon this one. So the total business, total GNSS business between 2019 to 2029, obviously before the pandemic era, it was expected to be 2525 billion euros multiplied by 90. So 2525 billion into 90, that much of Indian rupees. So the global market, it is expected, I have taken it from the GNSS market report itself. So it's a huge market. It's a huge market. So these are the consumer solutions. That means GNSS chipsets integrated in your handsets and your smart devices. Okay. And This is the road applications where you can see road and road. That means both road and railroad included. So these are the applications. So intelligent transport system is another area where GNSS has huge business potential. And the other 6.7%, although it's not very small amount, it is 170 billion euro. That they are the other things. Agriculture, a large part, drone, maritime, critical infrastructure, manned aviation, spacecraft, rail, emergency response, and geometric services. Okay, so it's a very large market. And if you go through the report, it has been told that the South Asian region would be the activity hotspot of for the GNSS market. I'd rather say the GNSS market endeavors and the activities were to take place. So India is lying there. Still now, the GNSS market in India, other than the research and development, what is taking place, mostly in case of government and academic research areas, there is huge market which is open for the business houses that can be taken care of. And obviously, there are huge potential for the academic institutions and the research laboratories to cater their need so that to come up with low cost, compact, low power consuming solutions so that our companies, our industries can directly take the solutions from us and take it to the market so that it can be used for these areas. And also, it has been told that the market would be dominated, the whole GNSS market would be dominated by consumer electronics. One of the major areas is the smart mobile phone or smart handheld devices, where GNSS chip below $5 GNSS chip would be a major component. So, while discussing or doing research or coming out with solutions in case of GNSS, one must understand, at least should have a basic understanding of the growing and ever expanding GNSS market, which has a very large potential of business. I think I have given answer to my already open question, and that's why, other than strategic reasons, so many countries interested to, I'd rather say, to have their share into this very large GNSS market and developing their own system. And the GNSS market macro trends. The timing solutions, a very large market. Geodetic solution, maritime, aviation applications, road, rail, agriculture, surveying, etc., etc. And they would have used in smart city applications, transport and IoT applications, for example, connected vehicles, consumer electronics, healthcare, intelligent buildings, manufacturing and supply chain, retail and leisure, etc., etc. Obviously, two important areas would be drones and UAVs, because the drones, when the number of drones should increase, definitely the drones should have their very precise location. Otherwise, number of accidents would enhance. So there lies the market for the drones, and obviously geolocation for the drones. And other areas is because the pandemic, it has shown us in many cases the mobile health, that means mobile phone based health or the e-health, its service can cater the need of a large number of people, not only daily maintenance of their health need, but in case of emergency, for management of healthcare professionals, efficient management of the very small resources. For example, I've got a small team of doctors, paramedics, and healthcare givers, nurses, etc., etc., and only 2 ambulances. In the Indian pandemic case, we have many patients, and everybody's need was there. So using mobile health, that team could access what is the nearest location where we are, and using a proper app, they can access where we are and where is the point of the nearest patient and what is the best possible route. And using the very same app, they can judge their patient, have the first triage, and okay, patient number 1 is not too serious, so we should rush to patient number 2 whose oxygen level is falling fast. So you can very well think of this type of application both from the hardware point of view, from the application Android-based app development point of view, also wearable sensor devices. From the wearable devices, the data can be collected and directly sent to the doctor's app. The doctors have a fast look into the vitals and can make the decision, so that the small resource can be very effectively utilized for the benefit of the society in a much efficient way. So these are the market macro trends what is coming in front of us. Another topic I should touch upon, that is GNSS on Android smartphones. Since Google Location API 24 onwards in Android 7, the mobile phones, the smartphones, which has got inbuilt GPS or GNSS chips, nowadays GNSS chips, we have not paid, already we have paid. Now, if we use the mobile phones as a receiver, we can get GNSS raw data other than the NMEA data there. So there are different types of data. NMEA data, it is ASCII data, directly gives the latitude, longitude, altitude, time, etc. And there are GNSS raw data, of which I talked about at the beginning. So the GNSS raw data, now using Google Location API 24, it is which can be implemented on Android 7 onwards, one can collect GNSS raw data. That can be used, number one, for the research purpose, and that can be used also for different types of GNSS-based app development. So Android-based cellular mobile phones with GNSS sensors can be used for geolocation. Okay, any user directly can download some app. I will talk about that. Download some app, get his or her own location. They can even log the NMEA data, the ASCII data, and send it using the GSM connectivity, send it to his or her own lab or to its group members. So for developing different types of app, for example, natural resource monitoring, a geolocation tagging is possible in case of the GIS infrastructure, what we are doing. It can show instantaneous location and satellite information. It can be used to collect NEMA data and raw data. Enhancement of user base and crowdsourcing needs sensitization. More and more people should be sensitized that how the mobile phones can be used. For example, in a smart city, we are crowdsourcing where there is waterlogging. Okay, so I am taking a snapshot of the waterlogging. Automatically, our geolocation is being waterlogged, and I am uploading the information to our corporation website, the corporation apps. So the corporation can map now with the geolocation that, okay, these are the areas where huge waterlogging there, and they can manage the resources for getting clear of the problem. So this way, proper crowdsourcing apps and the I would say no-cost GNSS receiver can help managing the system. So I'm giving you non-exhaustive example of different GNSS apps. You can go to Google Play Store and download this. GPS Essential, GPS Status Toolbox, GPS Test, GPS. One is GPS Space Test, another is GPS No Space Test. GPS Info, GPS Status, GNSS View, etc. Lots and lots of there. And here you can see your. So these are the satellites. So these are the satellites CNO, and these are your location. Okay, but you cannot log data here. In the next steps, for example, NEMA tools, GNSS tools, GNSS NEMA Tool Pro, Alta GPS Logger, PPM Commander, etc. So using this data, you can see we are getting the GNSS raw data. Using the GNSS raw data, we can save it into our handset and afterwards use it. For example, when while I was moving in aircraft from Kolkata to Bangalore, I took the data using this type of app from my aeroplane window, and after that, my team members created the trajectory. I could not collect data because it uses up lots of space. So you can see the plane's trajectory. You can see how it is moving. It can be seen. So this type of application can be done. So there are many GNSS apps. We will try to cover at least a bit in our hands-on session. So I have taken some data. This is it has got augmented reality. I have taken the snapshot from just in front of my house. So augmented reality is there. Galileo PVT. It's from ESA. Beautiful software. You can download and start using. More resources are there in the GSA website. You can go and download here. And NavIC-enabled Android phones, it was launched in Q2 of 2020. Many phones are there. A few examples I have given here. Also, more models has come. A question I am always asked: with older devices can receive NavIC support through a software update? Sorry, the answer is no. You have to purchase a new NavIC-enabled chipset enabled phone. For example, Snapdragon 865, etc., or Kirin 990, 990 5G SoC from Huawei. They should contain this one. Okay, so now the issues are jamming and spoofing. I think Madam Shweta and Dinesh will cover some part of it. So now we are depending much upon GNSS. So how resilient our infrastructure is, how vulnerable our infrastructure is, because we are putting a lot of money and we are putting a lot of dependency on this one. It should be secure, it should be resilient, and it should not be vulnerable. So these are the major issues, because on the right hand side I have shown you a GPS jammer. Okay, so the GPS jammer, you can purchase, although it's illegal, it is selling in India, it's illegal. But if you can go to Amazon or any other store, you can purchase it for rupees 700. Simply push it into your car dashboard, and for nearly 20 to 25 meters, all GNSS signals are jammed. And also another thing is spoofing. Spoofing means giving you false location. Somebody, your enemy, wants to give you false location. So it is transmitting GPS-like signal, and instead of getting your real location, you are getting a spoofed location. That means a false location. So we have to protect our system, our infrastructure from intentional spoofing or jamming, and also unintentional spoofing or jamming. Because number one, we have put a lot of effort and money, and number two, we have started using with high degree of confidence this infrastructure. So we have to. It's an open research area where people can still work how the hardware and software can be developed. And the recent trends is in use of compact multi-GNSS, multi-frequency RTK-enabled GNSS module, dual-frequency GNSS-enabled Android devices, Android phones, some of them are dual-frequency enabled, low-power GNSS module for IoT, interference jamming and mitigation technique, regional global RTK PPP service from space. Now we don't have to rely upon our own satellite. Some, for example, Terastra from Novatel, they will provide you paid service in L-band for correction services. Similarly, Galileo high accuracy service. So these are the trends of what is going on. And we people who are here, we can add up into the value-added service providers who's, to improve the access and use of GNSS. In the GNSS downstream value chain, we may be a major player. Dr. Atul Shukla will talk more about the opportunities in research and researchers and students, hardware integration, sensor subsystem development, antenna development, location-based application development, app development, software development. Please visit our software. We have some softwares. Some of them we are distributing free of cost. Some of them we are working with some of the industries. Algorithm for solution quality enhancement, for example, DNavIC, differential NavIC, atmospheric probing, spectrum protection technique, and Android-based app development for GNSS NavIC. The last point I want to touch upon, that India is a very good place for GNSS research. We are living in such a location that, so this is from Western India in 2019, we are seeing 50 satellites. Here it's our place. Once again, we are sitting 54 satellites. So we are using GPS, GLONASS, Galileo, Beidou, NavIC usages. So the Asia-Oceania region is a multi-GNSS signal hotspot, and using a GNSS view app screen from my home, I went to my rooftop and make it on, and you can see so many 34 satellites like that I can see. So my point is, we are living in a location where getting signal is very easy. We are living in a time where getting low-cost solution is easy. We are living in a time where very good software developer and apps developer are there. And also, we are living in a difficult time where people need support to sustain their life and also to enhance their quality of life. with people here, both from academia, industry, and R&D organization, from government and non-government. I would request you to join hands together. Let this workshop be another platform where we have some handholding so that we can use this excellent technology for the benefit of the people of our society and the country as a whole. I acknowledge our sponsors, Space Application Center, ISRO, AICTE, DRDO, DRDO ITR, and SAB-DST. And this is our team. And on behalf of all the team members, I thank you all for your kind patience and hearing over a long time of 2 hours. Thank you very much. Now, if you have any question, I will try to answer it. Maybe already we are late for lunch. But still, if there is 1 or 2 quick questions, I can take it, or I'll be here and other experts would be there to answer many of your questions. I think let us keep our questions on hold. If there is 1 or 2 questions. Please.
Sir, please check the chat box session.
Okay. One question is, I would like to know more about use of GNSS in electrical transmission. I will take. I will answer your question because it would be. I'd rather say, a bit time taking. So definitely, I'll try to answer your question, and I'll request, please note down your question. And many of my friends over the globe, they were kind enough. And from the country itself, they are very kind enough to spare their time with us to answer many of your questions. I'll put forward the questions before them. They can pick up the questions and answer some of your questions. And let us have some interaction session afterwards. Thank you very much once again. Kavita ji is asking one question: how is RTK different from differential GNSS? In one sentence, differential GNSS uses code-based measurement. So it is less accurate than the RTK. While RTK is using carrier phase-based measurement system. That is the basic difference. Both of them are real-time, but one uses code-based measurement, another uses the carrier phase-based measurements. So RTK is much more accurate. So to start with, this is the answer. Okay, Raj Hakkani, his question is, I'm doing my PhD on satellite navigation system. Should I contact you during my PhD journey if any query occurs? Obviously, we'll be happy to help as far as possible, not only during your PhD, but we have got very good network because it is a open topic. Any particular group cannot take up the challenge by themselves. You have got very good expertise in one field. Some other university or lab has got other expertise. We have got some expertise or some knowledge in one field. If we join hands together, that will be the real thing. Rakesh ji is asking one question. Please throw some light on GPS denied environments. Yes, in some cases, GPS denied environments, there are 2 things. Number 1, intentional jamming. There are GPS jammers from regulatory authorities, and intentional jammers are there. I can, in course of time, I will tell you a story. There are intentional jammers, or for example, in a government, maybe from a government regulation, GNSS jammers may be put inside a building, so the GNSS signals would not be there, or within a region, maybe 20-30 meters. Or in some cases, if you have got buildings, large buildings and trees on both the sides, and you are in a narrow road, which happens in cities. So you are in a GPS denied environment. What happens? The direct signal, the direct GPS signals does not reach your antenna. Only the multipath signals or no signal reaches your antenna. That is called the GNSS denied environment. So we need more number of signals and proper planning. What happens if GPS denial occurs? One example I already told, that INS integration, like that. Is there any possibility to design our own receiver for GNSS with available devices in the market? Well, if you talk about the GNSS chipset, I would, for a small laboratory, it's not possible because it's a very, very large thing. But many integrators are there who are importing the GNSS chipsets and putting it into their system. So you can design a system as a part of it. You can put the GNSS chipset there and develop your own system. Okay, Pratik is requesting study materials. Definitely, as far as possible, we have requested all the experts to share their study materials. Some of them has informed us that they cannot share it because of some regulatory problems. The PPT should not be shared, but we are recording all the sessions. The recording sessions should be uploaded and their link should be shared with you. Okay. Okay, if there is any more question. Is there any feedback form, attendance form to be filled up by us? No, attendance you don't have to fill up. Our system is collecting your attendance and the feedback. There will be two feedbacks, one from AICT itself, and we want to judge how we have conducted the course. Definitely we want to know your views and suggestions. So at on the last day, we will share your feedbacks. Thank you very much. Okay, so it's 2:01. Bon appetit. Have a nice lunch, and we will come together. Okay, another important question. Madhuji is asking, will there be any assessment? No, it is from Adityaji. Yes, there will be one assessment. Do not bother about it. It will be MCQ type, very simple type of test. Antenna design, no, antenna design we could not accommodate. Okay, well, let me request one of the experts to cover at least a few part on antenna technology. So bon appetit, have a nice lunch. We will once again meet back here at 2:40. Our session would start at 2:45. Thank you very much for your kind patience. Have a good time.